This is the Mathematics Education Podcast from mathedpodcast.com. Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and with me today is Julie Nurnberger-Haag, who's an assistant professor of mathematics education at Kent State University. Julie, thanks for being back on the podcast.
Thanks for doing this service to our field.
We are going to be talking about Julie's new study that is coming soon in the journal Early Education and Development, and the study is called A Cautionary Tale: How Children's Books Misteach Shapes. And it's a study of children's books about shapes, and it's going to be really intriguing, especially for me because I have two preschool-aged children. And so it's something that's a daily kind of occurrence for us to be talking about shapes and reading books. And before we get into your actual study with those shape books for children, what was the genesis of the study for you to want to take this on and to look at this topic?
I was teaching an elementary content course for mathematics for pre-service teachers. Mm-hmm. And I'd already started to understand from my elementary teaching colleagues that some people might have difficulty understanding or believing that a square was a rectangle. And so I posed that to my students to make sure that we addressed that, even though I wasn't teaching the geometry course.
Okay.
It was a number and operations course.
Yeah, but it's an important enough thing about squares and rectangles. We want to make sure we get this straight.
Exactly. So I wanted to see what would happen and help them out if I could. Of the 19 students that were in my course, none of them believed a square was a rectangle at that time.
Oh, wow.
So I really started thinking about the fact that they've had high school geometry and other experiences that still made it difficult for them to change their conceptions. And so I started looking back at, well, was it elementary textbooks, or where does this start? And so I went all the way back to children's books, since from birth, apparently, children are exposed to names of shapes.
What does the literature show? Like, so you had this anecdotal evidence with these 19, which is pretty striking to have 19 out of 19 that thought like square was separate from rectangle. Yeah. But what does the literature show about either children's or adults' understanding of shapes and shape properties and relationships?
For that specific issue, children and adults think that they're mutually exclusive for the most part. And then bigger picture, there are other issues with shapes as well. With children especially, they often conflate 2D and 3D shapes, like calling a cube a square, things like that. And especially with quadrilaterals and all the subtypes of quadrilaterals, research on pre-service teacher knowledge and teacher knowledge, as well as children, show similar things, that there's difficulties in understanding the categories and really thinking about the properties. They often tend to think in terms of prototypes from visual experiences.
Right, so this is like they have a vision of a triangle, and it's like a very perfect triangle sitting a certain way, like with its base along the horizontal.
Exactly.
And they think of triangles in relation to that prototype instead of thinking of like a general definition of triangle or general properties.
Exactly. In fact, one study, but reported for teachers in teaching children mathematics, that was Shifter in 1999, talked about a whole class of third grade students who were shown 10 different triangles, and the only triangle they recognized as a triangle was the equilateral or the acute isosceles. But then they went through and compared it to definitions and then accepted, okay, these are triangles, but the real triangles are the ones that were in their visual prototype.
So it's kind of this like, technically those are triangles, but I still like my ones that are closer to the prototype.
Exactly.
Yeah. You talked about how you wanted to kind of go back to the children's books to see where maybe some of these issues possibly were starting, or explore what was at least going on with those children's books. So how did you choose the children's books that you looked at?
I chose them from free and at-cost sources, thinking about what would be most representative for parents and teachers who might come to get these books. So I selected books from libraries as well as bookstores. And I took the two largest bookstore chains at the time and went to the local locations and went to two libraries, one in a middle to upper income town and one in a more urban town, so that I could try to get a range of what would be accessible to a variety of socioeconomic status.
And with the bookstores, were you able to kind of go to a category of books where that's called shape books and you could get like the most popular ones?
Not a shape book category.
Okay.
So I searched all the board books for anything that had shapes in it.
Okay.
And then also the juvenile mathematics shelves. So anything that was categorized as mathematics, then I looked for books that had shapes in it. And they didn't need to be a shape book that was entirely about shapes, although most of them were. It could have been Busy Bee book, for example, that was about numbers and colors and shapes.
Okay.
And then I would just look at those shape pages.
And so you ended up with 66 books, was that right?
There were 69 books about shapes, but 3 of them, the Tana Hoban books that most people who teach elementary would be familiar with, are just photographs. And so the coding procedures of trying to look for properties wasn't relevant.
Okay. And then now when you're going through these 66 books, how did you analyze what you were seeing on those pages?
Well, one of the ways I analyzed it was to use the Van Healy framework and looked for visual level, descriptive level, and informational relational level, depending on which term you want to use to describe that, since many terms have been used. Given that they were children's books, I didn't look for formal deduction or anything higher. And I looked for what shapes were portrayed, and then how they were portrayed in terms of the properties. Were any properties stated? Which properties were stated? And also how they were visually oriented on the page, things like that.
I'm speaking with Julie Nurnberger-Haag from Kent State University about her study, A Cautionary Tale, How Children's Books Misteach Shapes. So now that you've looked across those books, I'm very curious, what shapes did you see represented across the different books?
Well, most commonly, the shapes were squares, triangles, rectangles, and circles.
As expected.
As one might expect. But what I didn't expect was they really fell into 2 distributions of those shapes, which I called high-frequency shapes, that appeared in 65% or more of the books. But there were low-frequency shapes that appeared in 25% or fewer of the books.
Okay.
And many of those were polygons, like hexagon, pentagon.
Okay.
And then a few books did use the term quadrilateral, and then trapezoid, rhombus, and parallelogram. So the other quadrilaterals that aren't necessarily squares or rectangles fell into that low-frequency shape.
With rhombus, was it sometimes called diamond?
Oh, yes. But I only coded for a rhombus if the book used the term rhombus, not if it was a shape I knew to be a rhombus.
Okay. So you were using the label that book gave to it.
Exactly.
Yeah.
Yep.
And so calling it a rhombus was low frequency.
Correct.
But probably more books or other books had diamond.
Exactly.
Yeah.
And kite only appeared in 2 books as an actual mathematical shape. And so I didn't address that in the paper since there were so few examples.
Sure.
There were also 3-dimensional shapes. These were also low-frequency shapes. They tended to show visuals as well as properties more often than the 2-dimensional shape books.
Okay, yeah. And speaking of properties, so what did you see in terms of how the shapes were presented on those Van Healy levels that you mentioned? Like just see it by sight and that's what it is, or giving properties for it or relationships between them?
It was primarily just the visual. So there was a visual, either a photograph or a drawing, and a label of a shape name.
Yeah.
Even when properties were described, however, it was typically just the number of sides. So even if a book did try to teach children about properties of shapes, they really didn't address angles, even for words that I like to say were perfectly suited for this, like triangle and rectangle, where the root words of the actual term should lead us to think about angles a little bit. Most books didn't talk about angles.
One of the things that your study does is it gives a rundown of some of the inaccuracies that you can see or infer from the way that the shapes are presented. So I want to just ask you about some of those inaccuracies. What are some of the ones that really jumped out to you or that were so common that you couldn't avoid them in your analysis?
Yeah. One of the most problematic ones in my mind is the conflation of 2D with 3D shapes. So they would show a 3D object like a ball or a door or a toy box and call it a rectangle.
Or the ball, they would call it a circle.
Yes, thank you, sorry. So that was the biggest issue that is pretty pervasive throughout the sample. And there's several ways that the books did this conflation. I found sometimes it was the case like what we just described, where the image would better be described by by a three-dimensional mathematical term.
Yeah.
But there were other times where the outline of a face could have been the 2D shape, and then there was the case where there just really was not much resemblance. For example, a coat hanger. And
so what did they try to call that?
That's a triangle.
Oh, okay.
In these books, coat hangers are triangles.
Yeah.
Yes. Many, several of the books.
Right. So in that one, you'd have to do some real work to sort of see, like, we can try to see a triangle implied by this coat hanger thing, but it's kind of a stretch.
Or trace the inside, but be okay that there's rounded corners.
Yeah.
Instead of actual vertices with angles.
Right. Yeah, and the one about the faces of a three-dimensional shape, you know, that one, it's kind of like, it's nice for students to make the connection between the 2D faces and the 3D shape, but the books are kind of glossing over that entirely and just saying rectangle, or they're just saying triangle. Like, I think in your study you talk about cones and pyramids, and they just call it a triangle. Yeah,
so they're equating the object with the shape, as opposed to saying if you trace the outline, or can you find the rectangle on this shape. Very few books actually were nuanced in that language, which would have been more accurate.
What other kinds of inaccuracies did you see in the books?
Well, back to my original motivation about how are squares and rectangles treated.
Yeah.
43% of the books that actually describe properties of rectangles explicitly told children that two sides have to be longer than the other.
So for a rectangle, it has two long sides and two shorter sides.
Exactly. But not only are these explicit inaccuracies, there's implicit inaccuracies as well, because what typically happens is there is a rectangle page and there is a square page. And on the rectangle page, there would be no images of squares. So even if a book didn't tell children that a square is not a rectangle, it implied it by not having examples of squares as rectangles.
Yeah, square, that's over on that other page.
Exactly.
Not on the rectangle page.
And that relates to the issue of diamond that you alluded to earlier, where if a book talked about a diamond, which is a vernacular term as opposed to a mathematical shape, except Wolfram and one curricular series I found in Australia that treat them as actual shapes, they would show squares on one page and then rotate that square, and it would be a diamond on another page with a different label. So the books were also teaching children that orientation matters in shape.
It changes the shape.
It changes the shape. And this is at a time when children are learning how to write their letters and numbers, where orientation does matter.
Right.
So it's even more likely that they would come to believe, implicitly or explicitly, that orientation matters for shapes. So we need to be explicit with children that orientation doesn't matter with shapes.
Yeah, I've had this conversation with my young boys where they'll see tiles on the floor, and so when they're oriented to it one way, they'll call them squares, and then when they're oriented this other way, they'll call them diamonds. And so I use that to try to start a conversation with them. But yeah, I can see that it comes from these shape books where there's the diamond page. And so yeah, that would be another question too, of recognizing that a square is also a rhombus, a square is also a rectangle.
Right.
And a lot of attention, like you said, goes to the square rectangle relationship.
Right.
But we have probably the same issue with the square rhombus relationship.
We do, and we also have another issue with rhombuses, where several of the books will tell children that rhombuses cannot have right angles.
Okay. Wow.
So then, of course, by definition, a square couldn't be a rhombus.
Yeah. So maybe I'm wrong. Sorry.
No. So it's just another example, with the rectangle definition, that I shouldn't say definition, because I did code separately if they list properties or if they actually give a definition.
Oh, right.
But they're giving inaccurate properties, as though a rhombus can't have right angles.
So speaking of definitions, one thing that's in sort of my definition of polygons of any kind is that they're a closed figure, and then they have certain properties and everything.
Right.
So how did the aspect of being closed play out in the books?
A few books actually did mention that it should be closed. However, with the visual images, there were several inaccuracies, such as musical triangles being treated as mathematical triangles and labeled that way, whereas clearly they're not closed, and they have rounded corners, and they're actually 3D. So that relates to the 3D issue again.
Right. But they're called triangles.
Exactly. And so I actually use that in my teaching.
Yeah.
I ring the bell, and a prompt is, how is a mathematical triangle different from a musical triangle? And have the students talk about that in my pre-service teacher classes.
Yeah. We also talked about earlier about the classification where square is, a kind of rectangle. One of the inaccuracies you brought up in the paper has to do with trapezoid. I was wondering if you could say a little bit about that.
Yeah, so with most of the quadrilaterals, we have the issue where the most general case is the one that they label as that. So a parallelogram will not be portrayed as a rectangle. It'll only be portrayed with slanted sides, for example, to use vernacular terms.
Or even the rectangle page, it's non-square rectangles that they put on that page.
Exactly.
Yeah.
But we have the reverse issue with trapezoids, where the most specific case of an isosceles trapezoid is pretty universally the only example of trapezoids that are offered. And so they're only labeled as trapezoids. And so just like the pattern blocks, that will reinforce that trapezoids are only trapezoids if they have two sides congruent, is the perception,
right.
Which is inaccurate, of course.
Yeah, and so you saw that in the books. I've seen that with actual undergrads, where if I draw an isosceles trapezoid, they'll be like, yeah, that's a trapezoid. If I draw another one, they'll be like, I'm not sure what shape that is.
Yep.
It's like, it's a trapezoid.
Yep.
Yeah.
Exactly.
And so that actually reminds me of what we talked about earlier about the literature on students and adults' understanding of shapes. In this study, you're not making any links between, the books causing students to have certain understanding. But what's your thought about what you saw in the books versus what you saw in the literature about people's understandings of shapes?
Right. Because I was analyzing the books, of course, I can't establish causation. However, if the children are reading these books based on the conceptions that we saw in the books, we should expect to see the very results that prior literature has found is true for children and even adult thinking. And people like you and I who teach have seen anecdotally as well.
Right. So now let's turn to parents. If parents have children that are learning about shapes right now and they're looking at books and they want to help their child avoid those misconceptions and limited understandings of shapes, what would you say to them now? You can talk to them. Some of them might be listening.
Okay. Well, if you really want to use books about shapes or already have some in your home, then I would suggest checking and making sure that they at least portray more than one image of a given shape and a variety of those images in different orientations, and that they don't make the 2D 3D conflation error where they call a cone a triangle and things like that. And if you want to read them with your child, then help them talk about the properties and how not everything that appears in a book is always accurate. So it actually can serve broader goals of helping them be critical consumers, that just because they see something on the internet or just because they see something in a book doesn't make it true.
Yeah.
And talk about how these shapes that are shown as triangles or circles are actually similar or different from mathematical triangles or circles.
So maybe if a parent is realizing, there are some of these inaccuracies in the book, use it as the start of a conversation with your child.
Yeah.
And I think that could maybe be productive in some ways. I'm thinking about something I just saw recently where I think the Pediatric Association or whatever, they released new recommendations for screen time with preschoolers and young kids.
Okay.
And they said you should still kind of limit your screen time, but they said that screen time can be beneficial if an adult is watching the show or doing the thing on the screen. If an adult is doing it with the child and then talking about what they're seeing and interpreting it together, and that can have some real strong benefits. And I wonder if it's similar with these shape books where it's like the book has some inaccuracies, but if it's a start of a conversation, that could maybe even be more robust.
And so those are open questions for research, and that's not where I'm going to focus time in the immediate future. And I would love it if others who are hearing this podcast and go to this article would take some of that work on.
Yeah.
I would foresee that one possible productive way to interact as a parent might be to have them trace with their finger, where can you see rectangles on this shape, but the building is not a rectangle.
Yeah.
It's a rectangular prism.
Right.
Things
or
like
if this coat hanger suggests the idea of a triangle, let's trace where we see the triangle, but it's not the coat hanger. It's sort of suggested inside the coat hanger somewhere.
and that it actually has rounded corners, so that makes it different from a mathematical triangle.
Yeah. Well, thanks so much for talking with me about this. It's a really fascinating study, and like I said, I'm really into this topic because of having my own young kids. But I want to ask you one final question. I always try to have a little bit of fun at the end, as you know.
Yeah.
So if people go back and listen to episode 1509, you can hear Julie and Sarah talking about another children's book study about number. And so that's also a fascinating one. And there I also asked you what you would do if you weren't in math education. But now what I want to ask you actually is, you are in math education.
Yes.
So what has been maybe the most memorable day on the job in your math ed career?
Well, actually, the most memorable day on the job was when I got to co-pilot a plane at Bowling Green State University.
And I'm not sure how that relates to math ed. How did you work your way into the cockpit?
Because I was I was organizing a STEM event to promote science, technology, engineering, and mathematics, and the aviation department was part of that event.
Wow.
And so I had to go coordinate with them, and they offered to take me up, and I was in the co-pilot seat, and they let me take the wheel for a little bit. So
Wow.
I went back to the office and said, "Best day of work ever."
That sounds very fun. So
Yeah.
Well, we're very glad to have you in the field, and keep up the good work. So this article will be available very soon, or maybe it's available already when people are listening to this, through Early Education and Development. Julie, thanks so much for speaking with us.
Thank you, Sam.